Yes, I welcome you guys and physical chemistry. We've started some area called the solubility equilibrium. This is under ionic equilibria. And under this, we are going to look at sparingly soluble salts. We are going to look at some effects of some conditions. For example, the common ion effect. We're going to look at complex effect, addition of a complex, and many other things. So to break down the thing, we're going to look at the solubility equilibrium and the solubility product. Solubility equilibrium and solubility product. Now, basically, when we talk about this, it is a very, 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 very big thing. But from the mere term solubility, we can reflect back and we define some of the concepts here. We can define what solubility is. But if we are to remind from ordinary level, you know, like when you get sugar and you add it to water, we form what we call a solution. Okay, we form what we call a solution. Therefore, we call sugar a solute and we call water a solvent. So maybe to begin with, we can begin by reminding ourselves of those terminologies where we have a solute. When we say a solute, when I talk of a solute, I'm trying to mean a substance which can either be a liquid, a solid can be a liquid, a solid can be a solid or a gas that dissolves in a solvent to form a solution. So when I say a solute, is that substance either in liquid, solid, or gaseous state, which when dissolved in a solvent forms a solution. That is what we call a solute. Then when we say a solvent is a substance that dissolves a solute to form a solution. In most of the cases, we used to say that water is the most common solvent used in chemical reactions. However, here we shall find different substances being involved. Then when we say a solution, we can remember that is a mixture of a solute and a solvent, meaning a solution is a solute plus a solvent. Then after having known what a solute is and what a solvent is and a solution, we've got types of solutions. We've got types of solutions and we've got what we call a saturated solution. A saturated solution. So when we say a saturated solution, is that solution that cannot dissolve any more solute at a given temperature in presence of any dissolved solute. For example, I'm going to define it, I'm going to write it here. For example, if I have water and if I have sugar crystals, if I put water and then I put much sugar crystals and some of it has not dissolved completely. So I will say that this solution is saturated because it cannot dissolve any more solid particles in presence of the undissolved solute particles. Okay? So it means that even though you add much, it will not dissolve it. So when we say saturated solution, you're trying to mean that solution that cannot dissolve, any more solute okay, that cannot dissolve any more solute at a given temperature, that is O level. At a given temperature, I'm using the idea of ordinary level. At a given temperature, in presence of undissolved solute. But here we are talking about solubility equilibrium. So when we are to define it, we are going to say, now in our terms of equilibrium, we are going to say is a solution in which the dissolved and undissolved solute are in equilibrium. Okay? Is a solution in which the dissolved and undissolved solute are in equilibrium. That solution in which the dissolved and undissolved solute are in equilibrium is what we call a saturated solution. Then we have got what we call unsaturated. Unsaturated. It means that an unsaturated solution can dissolve more solute particles at a particular temperature. That solution which can dissolve, okay, which can dissolve more solute particles at a particular temperature, we say that it is unsaturated. Then we've got the supersaturated solution. That one contains more solute particles than it can hold at the same temperature in the presence of undissolved solute. So the supersaturated, it contains more solute particles than it can hold, okay? Than it can hold. So basically that is a simple introduction that draws us back in our high school work. But now here, when we talk about solubility equilibrium and solubility product, I want you to look at an ionic solid substance dissolving in water. Okay, we are specifically talking about ionic solid substances dissolving in water. Okay, when an ionic substance dissolves in water, it dissociates to give separate cations and anions. All right, now these, as the concentration of these ions in the solution increases, they collide to reform the solid phase. So we are going to find this reaction when you're writing it. We are going to find this. I'm going to consider an example of what I'm talking about. This is an ionic salt. When it dissolves in water, it dissociates to give separate cations, to give silver ion and chloride ion. We have said that when the concentration of these ones in the solution increases, they reform the solid, they collide to reform the solid phase. And that's why we use partial alloys. This one dissociates, keeps dissociating to form ions. As they increase in concentration, they reform from the solid phase. Now, solubility product, as per the heading, only applies in sparingly soluble salts. So here we are going to specifically deal with the sparingly soluble salts. And those sparingly soluble salts are many, and among which include silver chloride itself. We've gotten lead 2 chloride. We've gotten calcium hydroxide, strontium fluoride, calcium iodide, silver oxalate, silver bromide, etc. barium sulfate, silver ethane dioate, etc. There are too many. So we are specifically going to be dealing with the sparingly soluble salts. Sparingly soluble salts. Now, such salts dissolve in water. And when they dissolve in water, an equilibrium is established between the ions of the salt in solution and a solid solute. This is what exactly I'm trying to mean. When silver chloride is a sparingly soluble salt, so when it dissolves in water, an equilibrium is established between its ions and its solid substance. Okay, and in this case, the solution is said to be saturated. Hence the definition that a saturated solution is that solution which, when dissolved in water, establishes equilibrium, or sorry, we can say saturated solution is that solution in which the dissolved and the undissolved solute is in equilibrium. The dissolved are these ones which are present in solution, and the undissolved is this solid. Okay, which keeps dissolving, producing ions. As the ions increase, they reform the solid back, it keeps dissolving like that. So an equilibrium is established between the solid and the ions. So when they ask you the definition of a saturated solution, tell me that is a solution in which the dissolved and the undissolved solute is in equilibrium. Then the solubility. When we say solubility itself, solubility, the definition of solubility. Solubility is the amount of a solute or the amount of a salt. Amount of a solute or the amount of a solute that dissolves in any given amount, or that dissolves in a given amount of a solvent. Solubility is the amount of a solute or salt that dissolves in a given amount of solvent, that dissolves in a given amount of solvent to give or to form a saturated solution, at a given temperature. So basically, just to know the type of salts we are dealing with, sparingly soluble salt. Then know what is it all about this solubility. When that salt, which is sparingly soluble, dissolves in water, it establishes an equilibrium between its ion and a solid substance. All right? And that is it. That is it about solubility. Now, solubility being the amount, it means it can be expressed in terms of concentration. It can be established as when we are writing the units, it can be established as grams per liter of a solvent, or it can be established in moles per liter. It can be established in grams per 100 grams of water or solvent, something like that. In O level, you looked at this unit, grams per 100 grams of water, because we are specifically using water. But here solvents we are going to look at solubility in different substances, solubility in water, solubility in another substance, and you are going to find that the answers after calculation, they are going to be different. So let me give you the general aspect, because basically you've known what solubility equilibrium is, and now let's see what is it all about solubility product. How do we bring in the point of solubility a product? How do we bring in the point of solubility product? I want us to consider a saturated solution. Consider a saturated solution. Consider a saturated solution of silver chloride. A saturated solution of silver chloride. If we consider saturated solution of silver chloride, an equilibrium is going to be established. You have silver chloride establishing equilibrium between its ions of silver and then the chloride ion. Or I prefer this equation. Silver chloride dissolves in water. We write aqueous to establish equilibrium and form silver ion and chloride ion. Your equation becomes wrong when you use a complete arrow. So we are forming that. Now, this is what we call, this is the solubility equation of silver chloride. Now, according to the law of mass action, okay? According to the law of mass action, according to the law of mass action, according to the law of mass action, the ratio of concentration of the products to the concentration of the reactants is equal to a constant. So K, our constant K, is equal to the ratio of the ions. If there was anything like a balancing point, you raise it up. But since there is nothing here, we shall have it like that. 10 times the concentration of chloride ion. These square brackets represent concentration. Out of the concentration of silver chloride. This is equal to a constant, the ratio of concentration of the product out of the concentration of the reactants gives us a constant. Now, since the concentration of an ionized solid does not change with the time, okay, I want to show you how this one gets eliminated, because in our final expression, we shouldn't be having this. And we eliminated in the fact that the concentration of the unionized solid, this silver chloride, does not change with the time. And therefore, we end up having K as concentration of silver ion times concentration of chloride ion. So if you have this, if you have the constant, OK, as concentration of silver times concentration of chloride ion, we call this one KSP. 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 Concentration, rather the product of concentrations of the ions. Concentrations of the ions, their product. So we have seen that it is KSP, and we call it solubility product constant. Solubility product constant. Some books will be denoting it as KS. KS, KSP, solubility product constant, or simply solubility product. So when you find solubility product constant, solubility product, they are the same. Now, this one would mean that the product of silver ion and chloride ion, of course, you can see that it is the ionic product. One can call it the ionic product or the ion product of the solid. So KSP can also be referred to as the ion product of the solid, but that is not the definition. We are going to look at the definition of KSP. And by considering these two, by looking at this example, you can generate a definition of what solubility product is, or what solubility product constant is. So we have KS, you can call it KS, KSP, you can call it solubility product constant, something like that. Now, when we are defining KSP or solubility product, I want you to consider a point like that example to derive a definition. KSP is the concentration of silver power 1 times concentration of chloride power 1. So when you're defining that, when you're defining KSP or the solubility product, we define it as the product of molar concentration of ions. Product of molar concentrations of ions present in a saturated solution, of a sparingly soluble salt, can say ionic salt. When each ion is raised, to an appropriate power, at a given temperature. Mole product, solubility product of molar concentrations of ions present in a saturated solution of a sparingly soluble ionic salt when each ion is raised to an appropriate power at a given temperature. That is the definition of solubility product. This lesson, we are going to deal with the writing equations and the expressions of KSP. Then our other lesson next time would be specifically calculations. Now, let's have some kind of practice here. Write the expression of solubility product of the following salts, indicating their units. Let's go through this practice. 1, barium sulfate. 2, lead 2 chloride. 3, silver ethane diowate. 4, silver chromate. 5, strontium fluoride. 'Strontium fluoride', aluminium hydroxide, I guess this is enough for us. So let's begin with barium sulfate. Solution, barium sulfate. Of course, to write the expression of KSP, it is very, very, very easier when you have first written the equation of solubility. Barium sulfate is a solid plus aqueous, establishing equilibrium for barium ions and sulfate ions. So that is the equation. Then the expression of KSP would be equaling to the product of molar concentration of the ions, so barium ion times a sulfate ion. This is 2 minus. Then they want units. If you have to write the units, it's very, very, very easy. If this concentration, of course, I'm going to tell you how to derive the units. If the concentration here was in moles per decimeter cubed, you're multiplying other moles per decimeter cubed. It means that the units will be moles square decimeter power -6. As simple as that. Because since you're multiplying, you sum up the powers by laws of indices. Then for lead 2 chloride, Roman 2 has lead 2 chloride. For lead 2 chloride, we shall have lead 2 chloride solid plus aqueous, establishing equilibrium, form lead 2 ions and 2 chloride ions. So the expression of KSP will be concentration of lead times the chloride ion to the power 2 appropriate power. Chloride ion to the power 2. So when you're looking at this, it means that if this is moles per decimeters cubed, this one will be moles per decimeters cubed, but square. So the units, this will be moles decimeters cubed times moles square, because this squares everywhere. So it will be moles square decimeter power -6. So when you are to come up with the final units, it will be moles cubed, because it's mole power 1 times mole square, that is moles cubed, decimeter power -9. That is what we are having. You need to learn what if it is moles per liter. If they give you units in moles per liter, the working does not change. The working does not change. And then silver ethane dioate. Silver ethane dioate. How do you treat silver ethane dioate? Silver ethane dioate is the same as silver oxalate. So you write silver and oxalate. Oxalate is C2O4, but oxalate has got valence 2, while silver valence 1. So this is silver ethane dioate or silver oxalate. It dissolves in water and establishes equilibrium. So you shall have silver ion and the oxalate ion C2O4. So when you're writing the expression of KSP, it's going to be KSP is equal to concentration of silver ion raised to power 2 because of these 2 times oxalate ion, so that your units still will become moles cubed decimeter to the power -9. Then silver chromate. When we say silver chromate, you need to know how we write a chromate. Silver chromate, still you write silver and a chromate. Chromate is CrO4, so a 2. Students, sometimes they fail this because they fail to connect. They fail to connect the formulas or the formulae. So plus aqueous shall establish equilibrium, form silver ion and a chromate ion. So the expression of KSP will be equaling to the concentration of silver ion multiplied by the concentration of a chromate ion. As simple as that. All silver ion is raised to the power 2. Yeah. Units are the same as above. Strontium fluoride. Strontium fluoride. For strontium fluoride, we shall have strontium, then fluoride. Strontium has valency 2, fluoride has 1. So strontium fluoride is this. Plus aqueous shall establish equilibrium with strontium ion plus fluoride ion. This is F minus. So your KSP expression is going to be equal to the concentration of strontium multiplied by the concentration of fluoride ion raised to the power 2. As simple as that. Lastly, for aluminum hydroxide, shall have aluminum plus aqueous, we shall form aluminum ion and 3 hydroxide ion. So that your KSP expression is the concentration of aluminum ion times the concentration of hydroxide ion, but raised to the power 3. So it means that if we are to look at the units, this is, let me use now moles per liter, moles per liter, and this is moles per liter also, but to the power 3. So moles per liter, it will be moles power 4, because this is moles cubed, moles power 4, then liter power negative 4. That's what you would have for aluminum hydroxide. If you were using moles per decimeter, it will be moles per decimeter cubed, then times moles per decimeter cubed to the power 3. It implies that it would be moles decimeter cubed times moles cubed decimeter, okay, to the power negative 9. Eh? So it is going to be moles power 4 decimeter power negative 12. Now, with this background now, I'm going to give you expressions. I'm going to give you much work to write. Then our next lesson, we start calculations when all of you can write, when all of you can clearly write the expressions. Okay, when all of you can actually write the expressions. So this topic is the most, or is among the amazing topics that that can change our lives if well understood. So you're going to write for me the equations and the expression of solubility product. Okay, so for each of the following sparingly soluble salts, write the equation for solubility of the solute in water and the expression for the solubility product. One, calcium phosphate. Let me write for you this. Calcium phosphate, PO4. Calcium phosphate has valence 2, or rather 3. Calcium has 2. So we have a 2 here and a 3 here. So it is a solid plus up here, since we are writing in water, we are writing the solubility in water. So we shall have 3 calcium ions and 2 phosphate ions. 3 minus, not 2, because the valence is 3. So 3 minus. So when you're writing the expression of KSP, it's going to be the concentration of calcium ion raised to the power 3 times the concentration of a phosphate ion raised to the power 2. So you're starting from here. 2 silver sulfate. 3 silver phosphate. 4 aluminum sulfide. 5 chromium 3 hydroxide. 5 magnesium hydroxide. 7 lead 2 fluoride. 8 silver iodide. 9 silver bromate. 5 10 silver iodide. 5. Let's do that. Then we start from this very point to do the calculations within this area. I wish you the best as you practice this. See you then.